Everyone, we're going to learn about series today. And so we'll start with a definition. Okay? A series is the sum of the terms of a sequence. It's the sum of the terms of a sequence. So given what we learned about sequences before, if you take those numbers that you get, that list that you get, and you add all of those numbers together, okay, depending on how many you have, um, that's what a series is called. Right, so there's a couple things we have to learn definitionally. Right, so first, the Greek letter sigma. We actually use a capital sigma. It looks like a sideways M. It's a Greek letter representing the sum. Okay, so whenever you see this, again, it looks like a sideways M. It is telling you to find the sum of a bunch of numbers. Okay, now, summation notation is kind of overall what we call this, and that's where we use the sigma. So if you have a list of numbers, okay, so we have all these numbers here and we're adding them all together. So remember, we use A to represent um, just a number in a sequence, and this subscript right here tells us the place in the sequence. So we're adding a bunch of numbers together, it doesn't matter how many. Okay, we can use what's called summation notation. So we use a sigma. Okay, and we place the function inside of the sigma right here. Okay, so this sigma is sort of relating to this function. It's telling us to take this function and add a bunch of numbers together. And now the index is comprised of the numbers on the bottom and the top. Okay, so this number right here, this 1, okay, k is just the variable. Okay, so k right here, that just represents whatever my variable is. This 1 tells me where to start. And where to start, what I mean by that is what number to plug in first. Okay, so in this case, 1 would be the first number I plug in, then I plug in 2, 3, 4, 5, 6, etc. Right, this up here, this tells me where to end. Okay, now the fact that it's an end doesn't really mean anything. Usually there'll be a number there. So for instance, just an example, if I had a sigma from k equals 0 to 5, that means that the first number you plug in is 0. The second number you plug in is 1, 2, 3, 4, and then you stop when you get to 5. Right, so these are the numbers that you would plug in this case. That's what the index tells me. Right, so if we go back to our summation notation, right, again, right down here, this just tells me what my variable is and the number that I start with. So my variable is k, and I'm starting with 1, and this will change. It doesn't matter what letter this is, it could be anything. Up here, this tells me where I stop, and then this is the function that I am plugging these numbers into. All right, let's do an example. So let's write out all the terms of this sum. Well, the function is 1 over k, my variable is k, and the first number I'm plugging in is 1, the last number I should plug in is 10. Okay, so I'm plugging in 1, I'm adding because this is a sum. The next number I'm plugging in is 2, then 3, then 4, then 5, then we'll do a dot 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 because I respect your intelligence. And the last number that we're plugging in is 10. Right, so you're going to plug in all the numbers from 1 to 10 and you're adding them up, and that's what this summation is telling us to do. Right, now what if you don't have a number up top? What if you have a variable like this? And sometimes there'll actually be an infinity up there. So what happens with that? Well, you just plug it in. That's where you stop. So in this case, my function is k factorial. My variable is k. I'm starting at 0. So the first number I'm plugging in is 0. The second number I'm plugging in is 1. The third number I'm plugging in is 2, then 3, then 4. Then the last number I'm plugging in is n. And that's it. Okay, those are the terms of my sum. It's actually impossible to write out all the terms of this because it's infinite. It's too big. Okay, I don't know where n is, so I'm just going to write out a couple terms, put an ellipsis, and then write my last term there. Right, no problems with that. All right, let's discuss a couple properties. So this is sort of like a new operation that we're learning. I know you already know how to add, but it's sort of a new operation. And there's a couple things we can do to manipulate this to make life easier for us. Hey, our first one is if you have a constant on the inside of your sum and multiplied to your function. So a sub k is our function or our sequence, and c is a constant, you can take that constant out of your summation. Okay, an example of that would be like if you, we'll just keep the index the same, but if you had like 5 times x plus 1. Okay, well, in this case, my function would be x plus 1, and I have a constant of 5 on the outside, so just to make life easier for me, I can take that 5, bring it totally out of my sigma, and then I just have my function on the inside. Okay, my next one is if I have two sequences or two functions on the inside adding together, what you can do is split them apart and give them each their own sigma. Now keep in mind that you do have to keep your index the same on both of these because they were sharing that. Okay, so kind of what we did is we distributed the sigma to both of them if you want to think about it like that. Your index is going to be the same. Okay, you're starting in the same place, you're ending in the same place. The only thing that I did was I put the plus sign in between and they both have their own sigma now. It's essentially the same thing as this. Okay, and you could probably guess on my third, but if there's a subtraction sign, you can do the exact same thing, except this time we're subtracting. Okay, and last one's a little bit weird, but you can actually take your sum and split it into two sums if you need to and just change your index. So what I mean by that is, say we're starting at 1 and we're ending at n, then you can split this using any number that's located in your index. So what I mean by that is, for example, say I have a sum, and we'll keep it simple, we'll just use x, from like 1 to 10. Okay, well, if I wanted to take this sum and split it into two sums, well, all I need to do is pick a number that's between 1 and 10. So you could split this between, say, I don't know, 5 and then 6 to 10, and that's totally fine. So what we're doing here is we're saying that the sum from of all the numbers from 1 to 10 is the same thing as the sum of the numbers from 1 to 5 plus the sum of the numbers from 6 to 10. Okay, we're still accounting for every single number. Okay, that's the same thing. Or if we picked a different number, so we go 1 to 7 and then 8 to 10, that would still be the same thing. Right, so this one you don't use as often. It'll come up maybe more next year, but this is something that you can do. You can split your index up. You just have to make sure that you account for every single number in your index. Okay, and moving on, there's a couple more formulas here, and these are just, honestly, you don't need to memorize these. These just make life easier, so if you want to, you can. These come from binomial theorem. So this is just a way to rearrange or rewrite a given series. So if I ask you to find the sum of a constant, then you're going to add that constant to itself n times. So however many times it tells you to in this index, that's how many times you're adding your constant together. So same thing as just multiplying. Okay, if I give you a function like x or k or whatever, like y equals x, y equals k, then what we're asking you to do is add together an increasing sequence of numbers. Okay, you're increasing by 1 every time. So, or a consecutive sequence of numbers, I should say. So we're adding a bunch of numbers together. This is another way of writing that, and then yada yada. So you can use this to help yourself find sums a lot easier and a lot quicker. So we'll do a couple examples together. So first, I want to find the sum of this thing. Okay, so k is my variable. I'm starting at 1, I'm ending at 5, and my function is 3k. Well, remember, if you have any constant, you can take that out of your sum, okay? And then at this point, I could go one of two ways, okay? You could either write this as 3 times, and then we're substituting 1 in for k, and then 2, and then 3, and then 4, and then 5, okay? And this would be an answer. Alternatively, you could instead use the formulas that we have above. Okay, so the 3 is just chilling, it's in front. But the sum of a linear, so just k, is the same thing as n times n plus 1 over 2. Okay, and in this case, n is whatever your index is ending at. So in this case, 5. So that would be the same thing as 3 times 5 plus 1 over 2. Okay, and this would reduce to 45. So either way, you should get the same thing. If you memorize this, then it's just a quicker way of getting to the answer, but it's by no means absolutely necessary. All right, one more example. So this time I have a cubic and I'm adding 1. So remember, if I have a plus sign in my function, I can split this into 2 sums. The reason why I would do that is because it just makes going about this a lot easier. In this case, I have a cubic, so I can use my formula. So my formula for a cubic is n times n plus 1 over 2 squared. Okay, that's what I'm going to use. And in this case, n is 10. 10 is the number where I'm ending. It's the end of my index. So for a cubic, I'm going to take 10 plus 1 divided by 2 squared. Hey, over here, this is a constant. So in this is the same as your formula number 5 up above. All right, so this time 1 is my c value. This is my constant. And so I'm going to take my c value, which is 1, and I'm adding 1 to itself 10 times. Okay, well, if you calculate this out, I get 3025. 1 times 10 is usually 10. So I get 3035 is my final answer. All right, that is it for this video. I will see y'all later.